So this is Jack Jackson. In this video, in this section, we will be introducing a t-test. This will be a one-sample left-tailed t-test in this particular one. And this works basically the same as a z-test with only a very slight modification. So if you watch my earlier videos about z-tests, you'll be able to pick this up very quickly. Just as there is a t-interval, which we usually use instead of a z-interval for computing confidence intervals for the mean of a distribution, there's also a t-test, which we use instead of a z-test when performing hypothesis tests about means. First of all, let's recall the conditions needed to use a t-test and a z-test. For both the z and the t, we're performing inferences about the mean of a population. For a z-test or t-test, one sample version, we're performing a test of hypothesis comparing a sample mean to a hypothesized population mean. For both the z and the t, the distribution of sample means must be at least approximately normal. This is satisfied when any one of the following conditions hold. The distribution of individual measurements is normal and nearly or very nearly so, even for small sample sizes. The distribution of individual values is a bit mound-shaped, free of outliers and not heavily skewed, and the sample size is at least 15, or the sample size is greater than 30 for nearly any distribution of individuals. We use a z-test or z-interval when the population standard deviation is known, when sigma is known, but when sigma, the population standard deviation, is unknown, we're going to use a t-test or t-interval. And so here we're talking about a t-test, and it's almost always true that you're not going to know this population standard deviation. So a t-test is much more useful in general than a z-test. So if we don't know the population standard deviation, what do? Well, we take the formula for a z-score, we replace sigma by s, the sample standard deviation, but when we do that, the test statistic is no longer a z-score, it is a t-score. It no longer has a standard normal z distribution, it now has a t-distribution of n-1 degrees of freedom, where n is the sample size. Same setup as we had for a t-interval. So here goes through the details of the construction of a one-sample left-tailed t-test. Okay, so we're going to go through this closely and see how this works, and then we'll check it with the built-in app on a TI graphing calculator. So the example problem, the recommended amount of sleep for adult human is 8 hours per night. However, student life publication of a university indicates the average amount of sleep of college students living on its campus is 7 hours per night. Well, perhaps we think that maybe that's not even right, that maybe it's less. So we take a random sample of college students and survey to see how many hours of sleep that they got per night. The data is collected and displayed below. We want to test the hypothesis that the students actually got less than the reported 7 hours of sleep per night. Use a alpha equals 0.1. So if we're going to call the publisher of the study a liar or say they're not got accurate data, we need to have some sufficient evidence to show that. So we're going to assume that they are correct, that it really is 7 hours per night, and use that to generate our test. So that's the null hypothesis. Now, first of all, we have to decide what type of inference to use and check the needed conditions. So we check the conditions for a t-test. We're performing a test of hypothesis comparing the mean of a sample against a given hypothesized mean. We have this. The population standard deviation is unknown. This is true. We need the distribution of sample means to be approximately normal. Since the sample size is only 10, we need to be reasonably sure that the distribution of individuals does not deviate significantly from a normal distribution. One way to check this is with the normal probability plot. So the details will follow on the next slide. We can use a t-test if and only if all three of these conditions check out okay. So here we do a normal probability plot. We type our data in, say, on a T84 and list 1 here, L1. We go to stat plot, turn on the plot, choose the last one here. Our data is in L1. Always choose x-axis here and this, and then do zoom stat, and we get this here. Well, it's not exactly in a straight line. There is a little bit of a waviness going on here, but it's pretty close. It's not highly non-normal, So this is, and the test is pretty robust with respect to our normality requirement. So a sample size of 10 should make sample means at least pretty close to normal. We can do the same thing on a TI Inspire over here. I put a spreadsheet, put the data in there, called the name of that column sleep, and then went to the data thing here, put sleep on this axis, went to the menu, chose the type of table or type of graph, and tell it a normal probability plot, and it produces some sort of a line of best fit as well as the plot. And we see that that's close enough that we're going to say that the distribution of sample means, if not the distribution of individuals, is pretty much normal. So we can proceed. So we state the null and alternative hypothesis. The null hypothesis is that the distribution of sample means are approximately normal with mean 7. And the alternative hypothesis is that mean is less than 7. Notice it says less than here, so that's a less than here, which is a left-tailed test. We're testing one sample against a hypothesized standard, hypothesized known mean, and so that's going to be a one sample, in this case left-tailed t-test. So the t-star test statistic, x bar minus mu over sigma divided by square root of n, has a t-distribution with 9 degrees of freedom. N minus 1 is 10 minus 1 is 9. So here's the graph of the PDF that you can see. It looks a lot like a standard normal. It's a t-distribution. We compute the following sample statistics. N is 10, which we could just count, and the mean is standard deviation, probably especially for standard deviation, be easier to run it through the calculator. So since I've already got the data in list 1 or in sleep, depending on whether I'm using the 81 or the Inspire, I can run the one variable statistics to produce x bar and s and n. So there's just 3 of these numbers we need. We need x bar, the sample mean. We need s, the sample standard deviation, not the sigma, the s. And the n, we need those. So those 3 things, and we'll get the same thing over here. Now we compute the test statistic, t star. It's x bar minus mu over s divided by square root of n. That's 6.5 minus 7 over the 0.99 whatever divided by square root of 10. And we get about negative 1.59, let's say. Okay, we can get that over here by using x bar and s sub x from our variables once we've already done the one variable statistics. So if we do the one variable statistics on the TI-84, we can then go to open parentheses, then go to variables, number 5, statistics, find x bar, hit enter, and then say minus 7, close parentheses, 7 being the mu, divide by parentheses s of x. Instead of typing all these numbers in, I can go to variables, choose s sub x there, divide by square root of 10, close that over parentheses, hit enter, and we got that. And I'm going to store that as t because that's our t value or our test statistic. If we want to use the critical value method, we have that option. That's to find the critical value. The critical value, since it's a left-tailed test, all of the alpha, all of the probability of a type 1 error is on the left side. Okay, and so the critical value will be a t value for this type of distribution, t distribution with 9 degrees of freedom. So the critical value c is the boundary of our critical region, so that the probability to the left is 0.1. So of course we just use an inverse t for that. C is just inverse t of 0.19. And so when it says area, that's the probability to the left, the area under the PDF curve to the left for this particular distribution. That's 0.1 and 9 degrees of freedom. And then paste that after we run our inverse t. And it gets us this, or if you have the TI-83, might not have this screen, you just type this in directly. And just remember the order. The probability to the left goes first, then the degrees of freedom, and it produces the critical value, which is a t-score of negative 1.38. Compare that to the t-test statistic, which I think we already have stored as t, and that t-star test statistic was about negative 1.59. We want to compare that to So that negative 1.59, we want to compare that to the to this inverse t. So again, we're comparing the t-star test statistic to this critical value. In this case, it's a left-tailed test, so if the t-star is to the left of or less than the critical value, then we're in the reject region. I've been shading that red in my graphs. So that is the region that's rejected. So in this case, we're in that. Negative 1.6 is to the left of negative 1.4, and so we have the conclusion is that we reject the null hypothesis. Okay, I like the p-value method better. So what is a p-value? Remember that in general, a p-value is the probability of getting a test statistic of the value that we got or something more extreme given that the null hypothesis is true. Since this is a left-tailed test and the test statistic is negative, corresponding to a sample mean less than the hypothesized mean of 7, we simply compute the probability of getting a test statistic with our t-star value or something smaller. This is found with the t-CDF function on the calculator. Here I used negative 100. I usually tell you to use negative 1000. Either one is going to work okay here. And instead of negative infinity, then you go up to the t-test statistic right here. If I've got that stored as t, I could just have entered t there. And then, of course, I put in degrees of freedom at the end, which is 1 minus the sample size. That's 10 minus 1 is 9. And so we get there. That's a p-value. And now we compare the p-value directly to the alpha. Alpha is 0.1, p is 0.07, p is less than alpha. We reject the null hypothesis. So once again, we make a decision. If we use the critical value method, we're comparing the t-test statistic to the c, the critical value. T-star is negative 1.59. That is less than negative 1.38 for the critical value. Since this is a left-tailed test, the t-star is to the left of the critical value. That is enough to reject the null hypothesis in favor of the alternative. In the p-value method, we compare p to alpha. The p-value is approximately 0.07. That is less than the alpha of 0.10, and so that 7% less than 10%, p is less than alpha. That's enough to reject the null hypothesis in favor of the alternative hypothesis. So note that you can either use the critical value or the p-value method. We'll get the same conclusion. You don't have to do it both ways necessarily unless the question asks you for that. You could do one or the other. Generally speaking, I like the p-value method better, but either one works. If we can illustrate both of those methods together here. Here you see the t-distribution, the distribution of these sample statistics, the t-star values. Here's our actual t-star that we got, negative 1.586 right here. It's in the red region. The boundary of that red region is our critical value, C, which is about negative 1.38. The area to the left of that is alpha. That's the red shaded area under the PDF on this top graph. And we see that the test statistic is in that red region. When it's in the red region, that is the reject region. That's where we do have enough evidence to assume that the null hypothesis is false. Compare that to the illustration here on the one down here. The boundary of the region shaded here is the t-star test statistic, and that value is the blue area, which is the p-value. And now what we're doing is we're comparing the size of the blue to the size of the red. P are the size of the numbers, p to alpha. In this case, p is less than alpha. That is enough to reject the null hypothesis. So in either case, we reach the same conclusion. Let's state and interpret the conclusion in the context of the problem. The mean amount of sleep for students in the sample was 6.5 hours per night. This results in a p-value of 0.0735 from a one-sample left-tailed t-test. So at the alpha equals 0.1 level of significance, we see that there is sufficient evidence to conclude that the average amount of sleep for all students at this university is less than the hypothesized 7 hours of sleep per night. Note that in our conclusion, we include the sample mean, the hypothesized mean, the p-value, the alpha value, the type of the test, and our conclusion stated in the context of the problem. Next video, we'll do exactly this same problem, but we'll use a calculator shortcut app, and we'll see that we'll get the same conclusion.